that's okay, Becky. So hopefully Becky, as our technical whiz, will get us up and running on YouTube. And Zoe, if you're on the line, can I invite you to,
All right.
Take the reins.
Yeah, let me just share my screen for you guys. Get this started. Okay. Right, is that showing up all right on your guys' end?
It looks good, yeah. Thanks, Zoe.
Okay, brilliant. Right, so my paper that I wrote is titled The Identification, Investigation and Classification of Surface Depressions and Chalk Dissolution Features using an Integrated LiDAR and Geophysical Methods. Okay, so to start off with, just explain this was a student project for a taught MSc, which was then improved upon and adapted for publication. And the aim of this paper was to identify and characterize dissolution and anthropogenic target features using a combined approach of remote sensing and geophysical investigation. And for this, we used satellite imagery and LiDAR, and we also used electrical resistivity and ground penetrating radar. So the site that we focused on is in southern England in Hampshire called Holme Farm. And this is important because Holme Farm is located within the white chalk subgroup of the Hampshire Basin, which is an important aquifer and predominantly a carbonate, meaning that it's susceptible to dissolution and the development of widespread karstic features. And this is noteworthy because karstic features can be hazardous as they can provide pathways for groundwater contamination to the underlying aquifer. It throws site-specific contamination risks, and they also pose engineering hazards in the form of voids or infield voids. It's also differential settlement could be a risk due to uneven interface between chalk and soil cover. We can also get cavity collapse. And historically, for this aquifer, if you look at the work of Edmonds in 2008 on aquifer contamination potential, he said it was a little bit flawed due to the karstic nature of chalk not being taken fully into consideration, which kind of highlights the need for why we need to look into this. This is a photo here. Oh, let me just turn on my laser pointer. This photo here, we can see there's a small depression here in the Holme Farm field. Okay, so I'm going to go on to how do solution features form. Let me just get this up here. And so the main mechanism causing the formation of solution features is when we have concentrated accumulation of surface water causing the localized dissolution of chalk and carbonate bedrock. And topographic features such as valleys and depressions can act to channel and control the surface water and direct it, leading to focused areas of dissolution. And to be more site specific, I'm going to go back to Edmonds 2008. This is his figure here, which shows the progressive development of a dissolution pipe at the chalk Lambeth interface, which is the area that we're looking at. So I'll just go through it quickly. So we start with the London clay formation at the top, which is stopping any penetration of rainfall into the ground. And then once this layer is removed through erosion, we get this downward percolation of groundwater reaching this chalk interface here. And this is what would initiate the dissolution. And as this continues, we get this pipe which begins to extend downwards as the overlying material subsides. And this continues on and on until we get this surface expression here of the sinkhole feature, which is what we're trying to look for. Yep, that's the figure heading. Okay, so the site, Holme Farm in Hampshire, is located down here. And historic maps show that Holme Farm's existed since the 1860s. And also historic maps show that around the area we've got lots of disused chalk and clay pits, which would have been hand dug by farmers and used for fertilizers in the fields. And that's a little bit important for later on. So geologically, Holme Farm is situated on Upper Cretaceous and Paleogene sediments. And we have this predominant Tarrant chalk member, which is all over this area here. And it's categorized as a soft white chalk. So Tarrant chalk itself is fissured with two main discontinuity sets. So any groundwater storage and movement is largely controlled by these fractures, which results in a highly transmissive aquifer. We also have head and alluvium deposits present just due to a valley nearby, which is a well-developed river terrace system that was associated with the River Solent. And overall in the area, we have this gentle southerly dip of the chalk, which is going beneath these Paleogene cover, the Lambeth group, which means we get a rapid movement of groundwater to the south. And some tracer testing was done by Atkinson and Smith, and it recorded some very high velocities of this groundwater movement. So it's important because this is a major regionally significant aquifer, which is used for both drinking and agricultural purposes. Okay, so starting on the remote sensing side of things. So we initially used aerial photography dating from 2013, and this is a 0.25 meter resolution. And typically we can see these circular features here, which were identified on the surface to be solution features. And then we also, by combining this with historical maps, noted the presence of chalk and clay pits. And there's one just here, which has got some trees and shrubs within it, which is fairly typical of these chalk clay pits. So that was fairly useful to give us this initial overview of the site. And then moving on to the LiDAR data that we had, which was at a 1 meter resolution. We used this to generate hillshade maps. And this really opened up the area and gave us a good view of what we were meant to be looking at, identifying features which range from 5 to 80 meters wide, with got some of these general surface expressions here. And also from the LiDAR, it made it really easy to distinguish between the chalk clay pits, which we can see here, and in that field that I pointed out earlier from the satellite imagery. You can see the difference in their morphology, with these ones having a much sharper boundary from the deep coring within a small area, which really contrasts with the gentle sides of the dissolution features. And also, I'd just like to point out, historically, we noticed there are these field boundaries from the Bronze Age here, which you would never see without the LiDAR. You can see these pits located in the corners of these fields, because the farmers wouldn't want to transport the material over very long distances, which I thought was quite a neat thing to see. And finally, with the LiDAR, we had this Paleo Valley here, which we identified. It's got a northeast southwest trend. And that's important because it can act as a channel for runoff for groundwater and create a focus area for dissolution. So it's just another thing to note with that. Okay, and from the LiDAR, we derived a slope map. And this is just to highlight again the difference between anthropogenic features and these natural dissolution features here. You can see the much steeper sides in comparison. And also, a lot of these pits weren't marked on historical maps. So it's important to identify these, if you're doing a desk study based investigation. It's a very effective tool. So for the geophysical investigation, we used electromagnetic ground conductivity and ground penetrating radar with a 50 megahertz and 100 megahertz unshielded antennas. These are the traverses that we took on fields. There's a feature here, and here. We tried to do 2 per feature to give a decent representation of the morphology that we would see. And we also did some traverses in the bottom corner here, hoping to get some background levels of what we're expecting to see. Okay, so initially the traverses we took across the flat and undisturbed ground actually ended up identifying the Paleo Valley, which we noticed on the LiDAR. We didn't think it would extend that far into the field. And we can kind of see on the EM31 profile here, we've got this higher conductivity, which gradually decreases. And this is thought to represent the superficial infill within that Paleo Valley. And then in contrast, we've got the ground penetrating radar on the side here with 50 megahertz. And you can see this nice soil reflection horizon, given the curved valley feature here, which is an asymmetrical feature. Then we've got this infill in here, which doesn't appear to be particularly disturbed. So it's depth to the base of the feature we worked out to be 8.2 meters. We've also got this point interference here, but that's believed to be from some buried metal or something within the field, as it was an active field at the time. Okay, so I'm only going to show you 2 of the sinkholes that we looked at, because otherwise that would take up way too much time. So we have the EM31 traces here on the left-hand side. We can see this steady increase in conductivity as you move towards the center of the feature, which is fairly typical of dissolution features with a sediment infill. And that's the same for both of those on either side, getting to this background level here, which is shown in red. Then we have the Gpr results, which were very interesting. And we can see this jagged and fluctuating reflection profile. That's thought to be the presence of irregular rock head at depth of 2.6 to 4 meters, which would be the chalk. Now, if we move into the center of the feature here, we've got this discernible concave hummock with this disturbed infill within the topographic depression. So as well as this, we've got this disturbed infill cavities and some subsidence occurring. And the same thing is reflected in the 50 megahertz profile. But it didn't have as much penetration as the 100. We can see these shallow multiples of solution features on the edge of the boundaries, again, with that similar hummocky disturbed ground in the infill. Okay, so the second feature that we had was the largest on site, and it was 65 meters by 55 with a depth of 2 meters. And as you can see from the EM31 at the top here, we've got this increase in conductivity as we move towards the south. And the values would suggest the sort of clay infill. And this sharp peak here should be noted that could possibly be buried material or some kind of interference from nearby. And then with the traverse on the right-hand side, we've got this decrease in conductivity towards the center in comparison to the edges. And this sort of profile indicates a natural cavity. It's got asymmetry to it as well, which isn't really reflected in the surface expression. And if we look at the ground penetrating radar again, we've got this very irregular rockhead response, from the top of the chalk. And the Borum and Rolfe paper in 2017 interpreted similar responses in ground penetrating radar to be disturbed and brecciated chalk. And that ties in with the formation feature for dissolution, causing fissuring of the chalk and brecciation. So we've got these irregular horizons indicating disturbed infill and localized subsidence. Okay, so we managed to return back to the site with some permission from the landowner to do some soil augering, just get a little bit of ground truthing to see what we were dealing with beneath the surface. And we only had a hand auger, so it was a bit of a tough going one. But we can see we've got these clays and sandy clays beneath the organic soil horizon. And it was above chalk flint granular at the bottom, which we got. And we couldn't penetrate past the chalk flint because it was a hand auger and it was way too tough. But it was nice to see what was actually below the surface. And so from all of this, we put together a conceptual ground model for the site in which we've classified these dissolution features as buried sinkholes in accordance with the morphology suggested by Waltham and Foote in 2003. So we've got this disturbed infill, and which was determined from the ground penetrating radar profiles and the EM31 combined. We've got this irregular rock head again, cavity, brecciated chalk, and also the Paleo Valley infill with the head deposits. It also should be noted that with the boundaries here, we've got fairly diffuse boundary. That's what was observed in the field. And this is due to the Tarrant chalk being quite soft chalk. So typically, if this had been a harder chalk or a limestone, perhaps this would again given a sharper boundaries to the features and given a greater geophysical contrast in the ground penetrating radar and EM31 results. And also this model, we're giving it this southern dip, shallow dip towards the south with the chalk beneath the Lambeth group, giving this permeability contrast and area for concentration of groundwater and for dissolution. Okay, so in conclusion, the combined approach of the remote sensing and geophysical investigation we thought was highly effective in identifying and classifying the dissolution features, and it also allowed some identification of anthropogenic features and discerning them from the more natural features that we're looking at. which turned out to be much more widespread than was initially suggested with the historical maps. And so this is all very important. We need to, locate all of these features, as they can provide those pathways for groundwater contamination and engineering hazards as well. So the EM31 survey we thought was highly effective in the identification of dissolution features, but the ground penetrating radar, even though it gave us some good detail, it was still quite complex and difficult to interpret. And that we think is because of the presence of clay on the site, which would have attenuated the radar waves and reduced the depth of penetration, but still provided some really interesting information. And in the future, we think other geophysical methods of investigation for this kind of dissolution features could be tried out to determine if they'd be useful to integrate into this kind of approach. And in this figure here, this is the largest sinkhole, the second one that I showed you. It's quite a substantial feature. And just for scale, there's my friend there right in the corner, just to give you some scale of how big that is. Right, okay. So thank you for listening. If anyone's got any questions, then I'll have a look in the chat now.
Thank you very much, Zoe.
Hopefully that wasn't too fast.
No, it's impeccably timed.
Oh, good. Practicing, lots of practice.
Yeah, you would not know that was one of your first presentations. That was great. Thank you very much indeed, and congratulations again on being our prize winner for QJ-EGH.
Thank you.
Delighted to have you with us. And if anybody does have any questions on Zoe's presentation, please do submit them in the Q&A box.
Yeah, please let me know. I can get to them now or a bit later on, but don't have time.
I see something here come through on the chat, Zoe.
Yeah.
I think there's a comment here about asking whether or not there was any ground truthing.
Yeah, the only ground truthing that we had was with the hand auger, and unfortunately that wasn't directly in the field where we did the investigation. And that was, unfortunately, it was in the summer, and the farmer didn't want us disturbing his crops, which is, fair enough. But it was, I think it definitely ground truthing in the area within the features or nearby to the features would have been much more useful, so we can actually establish that depth of the rock head instead of just estimating it and things like that. So unfortunately, there was nothing more than the hand auger for the ground truthing.
Okay, thanks. Hopefully that answers the question. And I think there are some very nice comments for you there in the chat, Zoe. I'll let you enjoy those.
Thank you. Thank you. I appreciate it. Thank you for listening, everyone.
Okay. Thanks again, Zoe. And without further ado, I think we're going to move on to our second early career prize winner of the afternoon. And I'll invite Ross to join us. Ross Grant works with Equinor and was our early career prize winner on petroleum geoscience. So I'll hand over to Ross to give a presentation on his work.
Thanks. Let me just share my screen. So, yeah. Assume you can see the screen. So, this paper that's published in Petroleum Geoscience describes the structural evolution of the Brea area and details some of the research from my PhD thesis that was awarded by Heriot-Watt University in 2019 in association with the NERC Center for Doctoral Training in Oil and Gas. Since completing my PhD, I now work for Equinor as an exploration geologist. So to sort of get started and set the context and the rationale for the paper and the PhD research, the southern North Sea is a prolific gas province with over 60 years of exploration and production history, primarily from Permian rock ligand reservoirs and also upper Carboniferous reservoirs. The main play fairway outlines are indicated on the map here that shows the hydrocarbon fields across the region. As such, the area benefits from good data coverage in the basin center, where the majority of prospectivity has historically been found. However, vast areas of the basin margins and around the mid-North Sea high to the north remain somewhat underexplored and consequently less well understood. But the wealth of subsurface data now available provides new geoscientific research opportunities for hydrocarbon resources, but also for future carbon and or hydrogen storage opportunities. And this formed the basis for my PhD research that evaluated the geological evolution of this underexplored margin. So this is where Brea comes in. And the Brea field is this large gas field that's somewhat of an outlier that sits about 30 kilometers away from the main upper Carboniferous play fairway, but it proves a lower Carboniferous play. And this exploration success has challenged in the lower Carboniferous has challenged long-held views concerning the prospectivity of the lower Carboniferous across the region, and it demonstrates that the southwestern portions of the mid-North Sea high are prospective despite the absence of these Permian Rotliegend reservoirs and the source rocks belonging to the Westphalian coal measures. So this paper builds on the past work of Corfield et al. And more recently Bernard Besley, and investigates the controls on the structural and stratigraphic evolution of the Brea field, understanding southern North Sea gas opportunities out with the main Carboniferous play fairway, including the impact of Cenozoic uplift and the role played by evaporites through halokinesis and serving to detach structures between the subsalt and supersalt. And this study emphasizes the link between understanding the structure, trapping geometry, burial history, and exploration and production success, illuminating and opening up a poorly documented and unexplored lower Carboniferous play and petroleum system. So, in short, we show that the Brea field trap was a long-lived footwall high, affected by Variscan folding and uplift that truncated lower Carboniferous reservoirs beneath the base Permian unconformity. And then the drape of the structure by the upper Permian Zechstein evaporites then created this highly effective regional seal. The complexity of the overburden means that the accurate picture of the Brea structure only emerges after accurate depth conversion, accounting for important velocity effects within the overburden. The structure remained rigid through a polyphase deformation history of extension, inversion, tilting, and uplift. And the charge from lower Carboniferous source rocks that lie directly below the field is thought to have occurred prior to Variscan uplift, implying the field relies on a later charge, possibly long-distance migration. And then a pronounced easterly tilting during the Cenozoic affected the area and controlled gas migration into Brea from paleo structures and kitchens lying to the south and east. So we use public release 2D and 3D seismic and well data. And I'll demonstrate the key findings using two key seismic well transects that pass through the Brea field in here. Firstly, a west to east transect, the red line on the map right now, and then I'll later show a south to north transect, the green line, also on the map. And the lithostratigraphic column here kind of is just here for you to get your eye into what the colors are on some of the sections. So if we start with that first section, you'll see that there's quite some structural complexity to the line, and the stratigraphy comprises Paleozoic and Mesozoic strata. The base Permian unconformity, which forms a top reservoir level at Brea, sits just above the green and teal colors and truncates lower Carboniferous, fluvial deltaic, lacustrine, and shallow marine sediments at Brea that were deposited in a series of extensional basins. These can be seen as the blue on the map, the more regional map here. The upper Carboniferous primary source rock in the region is not seen at Brea, but it is encountered in wells to the east and also to the west and to the south as well. we can see how Brea sits in the footwall to this major downstepping terrace of faults here, and also that the Carboniferous is regionally deformed into long wavelength folding associated with that Beriscan orogeny. Erosion associated with this structural event has locally removed all the upper Carboniferous deposits from Brea, placing the lower Carboniferous sediments subcropping the BPU here. Then if we look at the overburden, we can see that it's quite structurally complex due to the presence of this thick Zechstein evaporite layer in here, and the presence of a major Mesozoic graben system in the center directly above the Brea field. The Zechstein forms this important detachment, decoupling structural styles from the sub-Zechstein section from the super-Zechstein section. And noticeable thickness variations which occur in the Zechstein are attributed to the halokinesis from thick salt. Seismic imaging of the Carboniferous is hampered in the graben areas where high velocity upper Cretaceous chalk and also Zechstein halokinesis occur. And accurate structural mapping is complicated by large lateral velocity variations which are associated with this graben, which preserves a thicker package of lower velocity sediments within its center. So the lower average velocities within the graben result in this push down in two-way time on seismic data. And when you map Brea in time using seismic, it actually appears as two structures. And you can see the lower velocities beneath the graben here at the base Permian unconformity level. However, equal gas-water contacts and pressure trends between these two apparent highs suggest one single structure. And therefore, when you do accurate depth conversion to interpret the structure, taking into account the velocity pushdown effect by the graben, it reveals Brea's true nature as this one single larger fault-bounded structure. And these findings underline the importance of detailed 3D mapping and overburden characterization in the identification of prospective, often subtle traps. And that's something that has explicit implications for prospectivity in the southern North Sea, and also in other evaporite basins where similar graben occur. And in fact, a larger closure can be defined within the 3D area than the gas-water contact of Brea, indicating that the structure is underfilled. And this is unusual considering that most of the structures within the main play fairway to the southeast are typically filled to spill. So it suggests possibly a charge limitation. And if we return to the seismic sections now, we can also bring in that south to north transect, which is the section now at the bottom. We can see several unconformities that truncate Mesozoic strata, particularly at the base of the Cretaceous here, the green line now shown, and also at the seabed. And these are associated with multiple tectonic episodes during the Mesozoic and Cenozoic that affected the area and are illustrated on the right-hand side on this tectonic stratigraphic chart. A subcrop map to that base Cretaceous unconformity, the green line, shows the effects of the tilting and uplift with a progressively older subcrop towards the north. And this unconformity coincides quite neatly with a significant doming event in the central North Sea that's quite well documented that took place around a similar time. Now, if we go back to the seismic line and we can study the seabed now, we see a variable subcrop there. And this is related to inversion during the late Cretaceous and early Cenozoic that affected the areas, particularly to the south of Brea. And if we take a seabed subcrop now, now, you can see it's possible to define a major northwest southeast trending anticlinal axis that results from the inversion of the area and uplift of the basement. But whilst inversion structures are quite commonly seen within the subsulc section, at Brea it seems that you see a lack of inversion structures and the area was just merely uplifted. And if we zoom out, we can see how that trend is regional across the whole of, well, most of the southern North Sea. And then finally, the final Cenozoic sort of tilting event, which occurred during the Neogene, can be seen from this Neogene subcrop here towards the eastern side of the southern North Sea that separates Neogene sediments from Cenozoic sediments below, and also the increasing age of bedrock towards the west on the eastern side of the UK. So all these events combined have repeatedly modified southern North Sea structures, including Brea, and are responsible for both trap formation and the remigration of gas between that highly effective regional Zechstein seal. So then how do we explain Brea, such a large working trap, but then an outlier? Well, if we study the gravity signature and geothermal gradients at Brea, we see a prominent gravity low and also an elevated geothermal gradient. So then to match subsalt temperatures and the maturities we see at Brea suggests a modest increase in radiogenic heat production from the crust, i.e. the presence of a buried buoyant granite that would help then explain the elevated nature of the area since the Carboniferous and possibly its long-lived rigidity due to from the Carboniferous to the present day. So that during uplift and tilting, the structure retained its charge, and due to the large structural relief in the western bounding fault serving to create a larger closure. So how do we put this all together, and what are the implications? Well, basin modeling shows that the Carboniferous source rocks reach their maximum burial and burnt out prior to the deposition of that key Zechstein seal. Present day charge from the source kitchen areas to the south is not sufficient to fill the structure to spill, nor is long distance migration from even further, from filling and spilling from other fields during tectonic restructuring. So it's possible that Brea was likely charged earlier during the deposition of thick Upper Cretaceous chalk when the source rocks in the areas to the south and to the east reached their maximum burial. So for prospectivity, but the underfilled nature of the field suggests that the original closure remained intact and that the structure did not leak during the punctuated episodes of restructuration. And this therefore reduces the possibility for updip prospectivity from leaked gas from Brea. But there remains a possibility for the remobilization of gas from other pre-inversion structures whose traps may not have remained so intact. So in the search for prospectivity, understanding the trap formation history both before and after numerous phases of restructuration and including regional tilting is important in assessing the charge potential for prospective structures in the region. So to finish, I'll leave you with the key conclusions and of course invite you to read the paper to learn more. And I'll also point out that I have two other publications from my PhD research, which this paper builds upon. And I'd like to thank the sponsors whose generosity have made this work possible, along with my co-authors for their support and contributions. And yeah, that's it. Thank you very much.
Thank you very much to Ross. Another great presentation. Really engaging, Ross. Thank you very, very much. And congratulations again on being our prize winner on the Petroleum Geoscience Journal. There are some nice comments coming in the chat and also some questions in the Q&A box. I don't know if you can see that, Ross, or would you like me to?
Yeah, I can see some of these. Yeah. So
there's one sorry, go on.
Be careful in saying that structures are filled to spill given the high degree of complexity and depth conversion, unless there is other evidence that migration is an issue. That's by Peter Drumgoole. Yeah, it's a very valid point. Yeah, there's obviously quite a an element of uncertainty associated with depth conversion. So yes, it's possible that structures aren't quite filled to spill, but yeah, I guess there is some evidence for several structures that they are possibly commonly filled to spill. But I appreciate your comment there. Yeah, I don't think there's any other questions. Just
Sorry, Ross. There are a couple. I don't know if you can see the Q&A box down there at the bottom. It is separate to the chats.
That's why. 2 questions.
It's confusing.
Yeah, from Phil Pushley. Since velocity is so important to structural interpretation, how did you obtain and can you see the velocity values from borehole seismic or just from sonic logs? Mainly from sonic logs. About that using, but yeah, we did QC the interpretation and depth conversion using the wells in the area. And secondly, do INEOS accept your interpretation of the Brea granite route? Well, we haven't had any dialogue with INEOS about this, and so maybe something they wish to contact us about. Yeah, so I'm not sure about that one. And yes, Graham Goffey says, a nice piece of work, Ross. I think I saw you interpret an intercarb extensional fault array on the western side of Brea. Is there any evidence for risk and reverse movement along this fault? There may be. It is possible that there could be some inversion along the faults, and it's something that we could look into with more detail. It's been a little while. I can't remember exactly off the top of my head.
Okay, fantastic. Thanks again, Ross. There are again some really nice comments on your presentation in the chat, and I'll leave you to enjoy those. If anybody does have any other questions for Ross, please do submit them in the Q&A or put them in the chat, and hopefully we can get to those. But thanks again, Ross. Thank you very much.
Yeah, thank you very much.
Okay, in that case, we will move on to our final early career presentation of the afternoon, and I'll pass over to Kit Hartman, who is our early career prize winner on the Journal of the Geological Society. So yes, and as with the other speakers, if you do have any questions for Kit, please submit them in the Q&A. Okay, thanks, Kit.
Thank you very much for attending my talk this afternoon, and thank you very much for the opportunity. I'm basically today going to be speaking to you about fissured networks, i.e. these networks of open cavities that tend to occur below regional unconformities and within basements. So before I go on, I should clarify our terms. The fissure, what do I mean when I say the word fissure, and what am I describing? Now, the initial images in your head that you have of things like great big cracks appearing at the surface of the earth, maybe in some disaster movie or other, to be honest, isn't far from the truth. When we look at modern examples of fissures in modern active tectonic regions, places like Iceland, where you see the Thingvellir Rift, the East African Rift has some fantastic examples. The Afar Rift there springs to mind. That's exactly what really we're seeing, these huge dilatant cavities open at the surface and ready for things to fall in effectively. Now, it was only relatively recently that we started to model these fissure systems and have a think about the physical processes behind them, really when the geologists started to take control of it. And it was some work basically out of Aachen University by Van Gent Holland, and they looked at the numerical and analog modeling, and they were able to show a really great link between the opening of these three-dimensional cavities, these bodies, these volumes of a fracture space that are intrinsically linked to shear planes in the subsurface. So we see this translation from shear at depth to tensile dilation at the surface. So now we've got our modeled examples and we've got our modern examples. Where are they in the rock record? If the physical processes make sense for modeling and we know that they exist in the present day, then surely they must exist in the rock record. And that's really where our research came in. I and my co-authors at Durham and here in Hull, we wanted to find some ancient examples of these so we could really get to grips with the structures that are involved and what they meant for sort of our Earth system. Now, we look at fissures for a number of reasons, but predominantly I tend to sort of group them into sort of two reasons. One is this ability that fissures can preserve information. It's a great preservation potential. If you think about them beneath these big regional unconformities, they're often cut by later cover sequences. All that sedimentary material that may have existed in that missing gap of time has been removed, but it can still be preserved within the fissures. And you find all sorts within them. You find huge vertebrate fossils in some cases, as well as huge amounts of sedimentological information, which can tell us about paleoclimate, that can tell us about all sorts of wonderful fluid chemistries and temperatures. So we can really get to grips with some of the more detailed basinal history events. Now, the other significant reason to study fissures is really their fluid transport and storage properties. These are the economic reasons to study fissures. They represent really quite voluminous spaces within the subsurface to store fluids, be they hydrocarbons or geothermal fluids, hydrothermal fluids, any kind of mineral precipitate that can sort of build up within these cavities, and equally for the migration, for the transport of these fluids. Again, be them hydrocarbons, or maybe we're looking more at a geothermal reservoir now where we're pumping down some modern fluids. They can actually be transported really well through these fissure systems. So to look at our fissure systems today, we're going to be looking at examples in Tor Bay down in southwest Britain. Now, Tor Bay is basically, we can think of it in two sequences for this talk today. Is a basement which consists of Devonian, really heavily folded limestone that was sort of deformed during the Variscan. Has a bit of sort of quartz veining and things related to post-orogenic collapse as well. But it's predominantly this beautiful blue-grey, really quite homogeneous limestone with occasionally interbedded slates, these sort of purpley slates. And then above that, we have our cover sequence. This is mostly the Tor Bay breccia formation, part of the Exeter group. These are basically new red sandstones, Permo-Triassic sandstones. Between those is our key horizon, basically what we're calling our base Permian unconformity or top basement. Okay, and here we find a huge amount of fissure sedimentary filled fissures. Okay, now these cut not just the basement, not just this limestone, but also the bottom few meters of that Permian sequence of those lowermost Tor Bay breccia formations. From when we look at the maps and the geological maps, one of the things we can see quite clearly is quite how fault controlled those geometries are. We have east-west faults, we have north-northeast, south-southwest, huge, great basin-defining, basin-bounding faults, and that's really what's defining the geometry and the shapes of our coastline. Now, we've done enough background, let's actually have a look at these bodies that I've been talking about. They occur all over Tor Bay and indeed further to the north up towards Petite Tor Point, and they are basically mostly occur within swarms. So those red boxes on the map there are where you find the most dominant swarms. You do find them in individual bodies further outside those boxes as well. And what we're looking at when we see them is a usually dilatant fault or fracture that is really pervasively infilled by bright red sediment. This sediment has bedding in it, it has all sorts of sedimentary structures, but predominantly it's rather homogeneous. It doesn't have a lot of internal structures most of the time. In a few examples, we see great examples of really well-preserved sedimentary structures, but for the most part, it's largely homogeneous. They occur mostly subvertically, but there are horizontal varieties as well. You can see one there in the top right-hand side. And also what we see pervasively is this great and huge amounts of calcite mineralization. When we look at the geometries of the body and of the fissures, and we can be assisted with things like satellite and low altitude drone imagery now to build 3D models, so we can have a look at these. And the great color contrast between the blue limestone and the bright red sediment means that these kind of techniques, these virtual remote sensing techniques are really useful in these outcrops. But what we find when we look and we collect our structural data is we have two sets, a north-south set of fissures and an east-west set. In general, the east-north-south set is basically slightly darker and is younger. Okay, they tend to consistently cross-cut the east-west set. However, when we look at the cross-cutting relationships there and we look at the timing with the overlying sequence, we can see that they are broadly contemporaneous. These are formed at two slightly different times, but are within the same regional events. The apertures of these bodies, when we look at them, the width effectively that we see, they can get up to about 40 meters wide. Mostly they're within the tens of centimeters range, but the apertures are huge and they vary wildly. So they can represent up to about 30% of the basement material can be fissure, which is not what you expect when you say the word basement. You think something impermeable, something crystalline. You're not expecting it to be about 30% sandstone. When we look and we use our sort of virtual outcrop techniques, we can actually begin to look at the connections between these bodies, both volumetrically, as you can see some of the plots there and see, and also as a set of line transects in 2 dimensions. Then we can analyze the nodes and the connections between them through topological analysis, and then get an insight into the degree of connectivity, at least in 2 dimensions. And what we see is that our fissure systems are incredibly well connected. They, at least in these 2-dimensional, these aerial views, they are exceptionally well connected. And that is consistent of all the fissure systems that we've looked at, not just here in Tor Bay. What fills them really is this bright red sediment, as I've mentioned, but there's a few key interesting facts about that. The first is that the sediment and the calcite mineralization is iterative. You might get a bit of sedimentation, some mineralization, a bit more sedimentation, some more mineralization. They are broadly coeval. So these fluids that are precipitating our calcite are around when we're depositing our sandstone. Now, when we look at the interactions between those veins and those sediments, for example, there in A, we can see that our vein, our mineral vein to the north, grows in almost perfect optical continuity with the cements that are holding our grains together. The grains you can only really ever pick out because of that lovely hematite coating that gives it its bright red color. We get these really quite porous sandstones, which is surprising given that they're within the basement, huge amounts of space. In many cases, like in C there in that image, they look largely uncompacted. You have a few examples, particularly in our horizontal fissures, where we have these sort of horizontal, subhorizontal structures, where we're not seeing coarser grains at all. We're seeing really a degree of fines that we're not finding within any of the other fissures, which was a bit of a geological problem. Why are the horizontal bodies containing a much finer, more homogeneous sandstone than the more vertical varieties? And we'll come on to answer that question in a bit. But especially since they're so connected, you can see those connections in the field. Those sediments are often homogeneous when you look at them. It looks like they've had all their sedimentary structures destroyed. But where you do see sedimentary structures, they're spectacular. So you see this wonderful jigsaw brecciation, textbook jigsaw brecciation, where it looks like you almost piece together all those clasts back together. It tells you a really sort of a fault wall implosion event almost. Where we have bedding, it's exceptionally well preserved, usually picked out by small changes in sort of normal grading across the sedimentary succession. What I love and one of my favorite structures is the geophysical fills. So these are basically little pyramidal piles of sandstone that occur within fissure cavities that must have basically had bits of sand that have piled up on top of a fault wall asperity or on top of a clast which was just contained within that fissure. So they're basically just preserved piles of sand within the rock record, which just goes to show the preservation potential we're looking at, as well as wonderful things like partial fills, which can give you great geophysical surfaces, cavity lining, textures where you see just gradual progression of sandstone filling from the outsides in. It almost gives you some kind of angular conformity, if that were to be a thing, as well as some more exotic stuff. So we get the odd fossil, you get the odd bit of volcaniclastic, bit of copper mineralization and all sorts stuck in there. They really are sort of chock full of all sorts of weird and wonderful stuff. As I've mentioned earlier, they are extensive calcite mineralization, but that calcite mineralization has pretty much every morphology under the sun to look at. Some of the most significant ones that I see were these scalenahedral and rhombohedral growths. Now, these were our classic nailhead and dogtooth spars. You can see them there between A and C, the classic examples in that. And even a weird, almost scalar fractal variety of our dogtooth spar, our scalenal growths, whereby we seem to have crystals growing on crystal faces. So scalenahedral dogtooth spars growing on the faces of other spars, growing on the faces of other spars. It was really quite a magnificent structure, and one I've still not quite got to grips with how it formed or why it formed. But the thing that unifies all our textures is that they are cavity filling. So we've started with a VUG, we've started with a volume, and we are precipitating calcite from the walls of the fissure and from the clasts within the fissure into the space. These are effectively syntaxial textures. Now that's really important because it tells us that we've got these big subsurface cavities with fluid percolating that are being gradually infilled by calcite. One of the most startling textures we see is what we call a Cockaid textures. Now, Cockaid comes, I believe, from the French, from rosette, so anybody familiar with Les Mis might recognize these structures. But effectively, they are concentric overgrowths around clasts within a fault cavity. So you think of a mineralized fault breccia with just rings and rings of different mineralization episodes. What we have in Torbay is lots of examples of these Cockaid textures, but also what we see is where they've been fractured and remobilized. The photo there on the left is fantastic because it's actually within a limestone towards the top of the sequence. And that class of Devonian mudstone, that DM in the middle there, is a much older piece of rock that's been fluid mobilized from the subsurface, pushed upwards, then mineralized around it in that white calcite, caught within the cavity, brecciated, so it's been broken. You can't actually see it in that photo, but the other half of that clast is round the corner. Then the sandstone is just poured in over the top of it. It's been caught and piled up. You can see the bedding beautifully in that. And then the whole system's been mineralized again by another phase of calcite, which is that sort of darker black one, and that's because of a carbon impurity. So you've got multiple phases of mineralization coating these clasts with, again, bedding and sedimentation happening in between these episodes. Our fluid flux events that we're talking about that form these Cockaid and these mineralization textures also have a really quite fundamental effect on the sandstone. Because we've got such a flux of fluid going through these fissures once they're filled with sandstone, they're elutriating the fines. They're picking up all the tiny little grains and they're bringing them either right up to the surface, up to the paleo surface, or they're dropping them out of suspension in lower velocity zones, i.e. our horizontal fractures that we mentioned earlier. We see actually, when we can see the links between the vertical and the horizontal, a great fining of material. And it's like all this clay and all the finer grains of sandstone have been filtered out through the coarser clasts and put into these horizontal storage areas. At those contacts, we see what look like tiny little sand volcanoes. Well, we term them sand volcanoes in the paper. If anyone has a better term, please do mention it to me. But they're basically these conical piles of sediment that's come up through the vertical fracture, hit a lower energy zone, and fallen out of suspension. And it creates this conical cone, often with sort of interfingering lengths of sandstone on top of it. So we're getting a real evidence for fluid flux, sorting, grading, and removing our fine material, which is only going to have a net increase on our porosity and a net increase on our permeability of these sequence. In addition, because these are fissures, because they're open at the surface, the really fine material will never make it in because it will be transported by its fluid medium, be it a wind in an aeolian sandstone, or in this case, a alluvial fan system or a braided fluvial system, depending on the different formations. Those waters are going to help hold those in suspension. They're not going to fall out of gravity. The really big grains aren't actually going to make it in the first place because they're not going to be mobilized. So you're going to have a narrower bias to the grains that are actually entering this system, again leading to this really well-sorted sandstone within the fissures. When we look at our tectonic associations, what we see is a huge amount of association with early Permian opening of the Portland White Basin. This is an offshore basin, which basically, as it continued to rift and opened, it moved progressively east. So this is a really early onshore opening of the Portland White Basin. We can reconstruct our paleo stresses by looking at the scratches on our fault walls to really tell us the radial extensive system and that our fissure systems are intrinsically related to our larger faults. Often they are within our huge faults. Some of the biggest ones we see are directly on these major basin bounding faults. So there is this intrinsic relationship between these large basin bounding faults, these seismogenically active faults, and the fissure systems formation. So I couldn't get away with saying both lots of fluid flux and seismogenically active faults in association without trying to marry the two, because I do think, and I believe there is evidence here for some kind of near surface model for seismogenic pumping in the near surface, i.e. some changes in the cavity geometries of these fissures, changes in the volumes, in the width, in the length, just as things are moving during seismogenic faulting will cause fluid flux within the subsurface. And that's what's helping to sort our sandstones, to precipitate our calcites and all sorts. When we look at the apertures, they're in excess of about, well, they go up to about 40 meters, which is really huge. So the capacity for storage and transport really is phenomenal. So I think that really is my take-home message, that if there exists basically within our top basement structures, in this case limestone, in other cases granites and tonalites that I've seen, a highly permeable fracture system. And these can preserve geological information for us to investigate, but also store, also transport fluids, and they are almost always intrinsically related to seismogenic events. Thank you very much, and apologies if I've gone over. I feel I have.
Thanks very much, Kit. That was wonderful. Great presentation. Congratulations again on your win. There are one or two questions coming in. I don't know if you can see the Q&A box, but we had a question in there. I would read it out. It is rather long, but if you want to have a quick look at those, and either, if you'd like to answer them verbally or feel free to type the answers in the box.
Yeah, so Tim's talking about the horizontal stresses, sorry, the horizontal structures in relation to sort of the stress regimes you're looking at right in the near surface. Because when you get to the near surface, you lose your confining stresses, really. You have a free surface right at the top. So the opening of these fissures or the opening of these structures really is are they related to these tectonic events? What are they related to? Are they just collapsed structures? And basically, I think they're effectively almost one and the same. So they are horizontal cavities related to the normal ones. But when you get up into that near surface, this subsurface deformation, these shear in the subsurface, when it's translated to tensile action in the near surface, you get really weird and wonderful cavities opening. They can be almost spherical in sometimes because everything's just collapsing and falling and moving around in itself. So you're absolutely right. These horizontal ones are right in the surface, and they more just represent large blocks of basement moving around in relation, collapsing, as you say, within these structures. And Jim has got the classic, yes, it's the karst issue. If I could include one more slide, it would be on the karstification. So what we see really is that the karst systems we looked at, and I looked long and hard for evidence of karstification, because those limestones really are susceptible. There are huge cavern systems there. They're chemically susceptible to karstification. So why aren't we seeing them in these fissures? And the truth is we see them in a few, particularly where we have really heavy fluid influx, some later mineralization related to movement on the Stickle Power Philosophy fault zone. We see some karstification there. But mostly our fault walls are really angular. There's no evidence for dissolution. We've got breccia class, these jigsaw breccias, no evidence for really loss of material. So I can't, other than the fact that maybe the fluids are completely already saturated from karstification elsewhere, or that the calcite is somehow shielding in regions shielding that basement from karstification, I don't really have a great answer for you, other than that I can conclusively say really that these are tectonically controlled. They're not karst controlled, but they are almost one and the same when you get to it.
Great stuff. Hopefully those answers there address those questions. Well, we're coming up to 4:30. So if there are any more questions for Kit, please do put them in the box. Kit, perhaps I can ask you to address those just in the Q&A box. And again, I would say thank you very much to Kit, to Zoe, to Ross, and also to my colleague Flo for their presentations this afternoon. Just quickly before I hand over to Richard, I would like to say that all three of the early career researcher prize-winning papers in the journals are free to read. I'll circulate links to those articles with the slides from the presentation. Yeah, so please do feel free to read those and access those. And I think I'll just hand over to Richard Hughes, our Executive Secretary, to give some wrap-up comments.
Yeah, thank you, David. And hello, everybody. I'm afraid I hit a major technical glitch about 3 o'clock this afternoon, so I was only able to join you about 30 minutes ago. Zoe, I'm afraid I missed your talk completely. Ross, I heard probably the last half hour of yours. And Kit, I had the pleasure of the entire show. So great talks. And can I offer my sincere congratulations to all 3 early career prize winners. And I will be making a note of looking at those open access publications over the next couple of days. Yeah, just a few words from me to wrap up. I'll be really very brief, but I know from not just, of course, my involvement with the Geological Society publishing house, but I'm also involved with Geoscience World, which is a US-based aggregator for scholarly societies. I know what a tough time it is for society publishing. It's a very competitive publishing landscape out there. We've got some big predatory commercial publishers snapping at our heels all the time. They have very deep pockets, enabling them to invest in platform development and other innovations that is frankly quite tough for us to match. But as I think back to 2020 and the work of the Geological Society Publishing House, frankly, I think it's a year in which we went from strength to strength. We got off to a flyer in February of 2020 when Maggie Simmons joined us, or was appointed rather, to our Director of Publishing and Information Services role. And it's great to have somebody of Maggie's ability at the helm of the publishing house. And there are so many highlights I could pick out really from 2020. But if there is one jewel in the crown, of course, it's the launch of our own open access journal. No doubt you've heard a little bit about that this afternoon, ES3. And great to have Catherine Goodenough as the editor-in-chief of ES3. And I look forward to seeing its success going forward. A point I'd like to make about the role of society publishers like the Geological Society is we all have a fairly basic business model in which any surpluses that we make from our publishing work are reinvested in our public good activities, which comprise basically a suite of things that we do to advocate the profession. So we do education, we do policy work, we do communications and outreach, and it's all funded in part through our publishing work. So none of this, of course, would be possible without the staff and without the volunteers, from the editorial boards through the reviewers of our papers to the authors themselves. And I just would like you all to bear in mind, we're incredibly grateful for your volunteer time, and we're incredibly grateful to people who submit their manuscripts to our journals. But please do bear in mind when you're doing so that indirectly you are supporting our science and you are supporting the profession. And my very sincere thanks to you all for all your hard work, much of it done in your own time, to continue to support the work of the Geological Society Publishing House, and long may that continue. Just finally from me, I hope very much this time next year, or when we do run a Publications Festival event in 2022, that we'll be able to meet in person. We're all working in remote parts of the country, perhaps internationally at the moment as well. And I do remember the days, it's not that long ago, when we all used to meet face to face at the Society's offices in Burlington House, and after the serious business had been done, we used to really enjoy informally chatting over a glass of wine and a few nibbles. I'm sure I'm not the only person who is very much looking forward to those days returning. So fingers crossed for an in-person event in 2022. And with that, thank you all very much again. David, have you got any very final words to say? I'm going to mute my microphone at this point.
Nothing more from me. I think you've summarised it all really nicely there, Richard. So yeah, just a big thank you again to all of our speakers and to Becky for her technical help. And of course, thank you to everyone who's come along this afternoon and submitted questions. I hope you found it a stimulating session, and we look forward to continued collaborations, as Richard says, on our publishing activities into the future. So I think we'll leave it there for now, and thank you very much and goodbye.